Hello everyone, myself Dr. Subhendu Sarkar. I am an assistant professor of the Department of Chemistry of Brunel University. Welcome to the second part of the video lecture of thermodynamics. So in this video, I have explicitly described some of the important thermodynamic functions and the four laws of thermodynamics. So let's start with the zeroth law of thermodynamics. So zeroth law of thermodynamics actually gives the concept of temperature, which is an intensive property as I described in the last video. So I have shown here three systems, namely system A, system B and system C. System A is in thermal equilibrium with system B. That means temperature of system A is equal to the temperature of system B, and if system B is in thermal equilibrium with system C, that is temperature of system B is equal to temperature of system C, then zeroth law of thermodynamics suggests that system A will be automatically in thermal equilibrium with system C. That means temperature of system A will be the will be equal to the temperature of system C. Now let us describe our first thermodynamic function, namely the internal energy. So the name suggests that it is the total internal energy content of the systems. So we know that all matters must have a storage of energy for its existence. So internal energy is represented by the symbol capital U, and it is the sum of total translational energy, rotational energy, vibrational energy, electronic energy, nuclear energy, potential energy, etc. associated with the constituent of the system. Internal energy is an extensive property and it is a state function. That means the change in internal energy is solely dependent on the initial and final state of the system. Since internal energy is an energy quantity, it has the same unit of energy, that is SI unit of joule. Now let us describe the first law of thermodynamics. So this is the basically law of conservation of energy, and this law introduce the concept of internal energy which I have just described. So say for example, here I have pictorially represented two systems, system A and system B. System A has the internal energy UA and system B has the internal energy UB. Say plus Q amount of heat is added to system A. As a result of that, system A is transformed to system B where it does some amount of work W. So the change in internal energy, which is UB minus UA given as delta U, will be equal to Q, which is the heat added to the system, minus work done by the system. So the enthalpy. So enthalpy is one of the most important thermodynamic functions, and it is basically defined as U plus PV. So there is a thermodynamic function which deals with heat changes at constant pressure, particularly for chemical process. So if we calculate the change in enthalpy, it is basically delta U plus P delta V plus V delta P. Now if we apply first law of thermodynamics here, which is delta U equal to Q minus P delta V, and put it in this equation, we will eventually get delta H equal to Q plus V delta V. Now if the process is carried out at constant pressure, that is for an isobaric process, this term will be eliminated and we will get delta H equal to QP, that is heat change at constant pressure. So this is the physical significance of enthalpy change. So enthalpy change is nothing but heat change of the system at constant pressure. Like internal energy, enthalpy is also an extensive property and it is a state function. That means we can calculate the enthalpy change of a system by subtracting the value from the final to the initial. Now let us deduce the relation between enthalpy change and internal energy change for a chemical process. So let us consider a gaseous reaction as N1A plus N2B equal to N3C plus N4D. So what is the change of number of moles? It is N3 plus N4 minus N1 plus N2. Now for constant pressure process, we can get delta H equal to delta U plus P delta V, and instead of P delta V, if it is an ideal gas, we can write delta N RT. Since delta H is QP and delta U is heat change at constant volume, we can write QP equal to QV plus delta N RT. Now for a process where number of moles change is 0, then enthalpy change and internal energy change will be equal. Now let us move on to the second law of thermodynamics. So let us ask a question: why we need the second law of thermodynamics? Because first law of thermodynamics gives the laws of conservation of energy and it gives the concept of internal energy. So why we require another law, which is the second law of thermodynamics? So let us ask this question. So what are the thermodynamic criteria for a process to be spontaneous, or what are the thermodynamic conditions for equilibrium? So to answer this question, we need the second law of thermodynamics. So there are several statements. I will mention the two important statements, which is one is given by Clausius and the other one is given by Kelvin. So I will just read out the Clausius statement. It is impossible for a self-acting machine unaided by any external agency to convey heat from a body at low temperature to one at a high temperature. And what is Kelvin's statement say? It is impossible to derive a continuous supply of work by cooling a body to a temperature lower than that of the coldest of the surrounding. So basically, second law of thermodynamics introduced the concept of entropy. So what is entropy? This is a thermodynamic properties of a substance which measures the disorderedness or randomness of a system. Entropy change of a system is given by the ratio of heat change divided by temperature in Kelvin scale. So remember that here the heat change is associated only for the reversible process, not for irreversible process. So where d cut q reversible is the reversible heat change at temperature Tk. For finite change at constant temperature Tk, delta S will be q reversible by T. So what is the physical significance of entropy? So this is a property of a substance which measures the randomness or disorderedness of the system. Solid substances are most ordered than liquids, which is more ordered than gases. Therefore, entropy follows this order. Entropy of solid is less than entropy of liquid, which is again less than entropy of gas. Entropy change is a perfect differential as its value depends only on the initial and final state of the system, independent of the path of the change. That means entropy is a state function, and like the other thermodynamic properties, internal energy and enthalpy, entropy is also an extensive property, and the unit of entropy is joule per Kelvin. So how we are going to calculate the change of entropy for an ideal gas? See, this is the equation for calculating entropy change, delta S equal to Q reversible by T. Now, if we substitute this by this, we will get delta S equal to NCV bar dt by T plus PdV by T. So, for ideal gas, PV equal to nRT. By putting this, we will get this equation. Now, for isothermal process, this term will go and we will get only delta S equal to nR ln V2 by V1. So, how we are going to calculate the change of entropy during a phase transition, that is from solid to liquid or liquid to gas or solid to vapor. So during a phase change at constant temperature, Q reversible will be equal to the latent heat required for the phase transition. Thus, entropy change for fusion process will be latent heat for fusion divided by the temperature at which the fusion is occurring, that is the melting point of the substance. Also, entropy change for vaporization will be delta S vaporization divided by boiling point of the particular substance. Now, let us describe a very important concept of thermodynamics called the Carnot cycle. So, this is an imaginary cyclic process given by Sadi Carnot. So, here the four successive reversible processes occurs in the order. The first one is isothermal reversible expansion of a gas. The second one is adiabatic reversible expansion, and third one is isothermal reversible compression, and the fourth one is adiabatic reversible compression of a gas. So this is the pictorial representation of the Carnot cycle. Say for example, the system is at state 1 with pressure P1, volume V1. It moves to state 2 with pressure P2, volume V2 through the process isothermal reversible expansion, and from state 2 it moves to state 3 through adiabatic reversible expansion where the pressure is P3 and volume V3, and then it comes back to state 4 by isothermal reversible compression, and then from state 4 to state 1, that is from P4 V4 to P1 V1 through adiabatic reversible compression. So this is the heat change involved for this cyclic process, and I have explicitly shown here the calculation of work done involved in each step. So W1 is this, W2 is will be this for the adiabatic process, and W3 will be nRT T2 ln V3 by V4, and W4 is this one. So total work done involved in the cyclic process is this one. Now let us calculate an important parameter of Carnot cycle called the efficiency of Carnot cycle. It can be defined as the ratio of net work done by the system with respect to the amount of heat absorbed by the system. So net work done is W and heat absorbed is this one. So if we substitute the value of W and Q here, we will get eta equal to T1 minus T2, that means 1 minus T2 by T1 minus T2 by T1, that is 1 minus T2 by T1. So let's move on to another important thermodynamic function called the Helmholtz free energy, designated as capital A. It is defined as U minus Ts. So if we put differentiate this equation, we will get this one d equal to minus PdV minus SdT. So now let us consider a change in A in an isothermal process. Then it will be delta A equal to delta U minus T delta S. Now if we substitute delta S with Q reversible by T, then you will get delta A equal to delta U minus Q reversible. Now from first law of thermodynamics, delta U equal to Q reversible minus W reversible. So delta A will be ultimately W minus of W reversible. So A or Helmholtz free energy is the maximum work done by the system. Our next thermodynamic function is Gibbs function or Gibbs free energy or free energy. So Gibbs free energy is defined as H minus Ts. Now G is also a state function. It is a perfect differential and extensive property like the other thermodynamic function. So if we do a little bit of algebra here and using first law of thermodynamics, we will eventually get dg equal to vdp minus sdt. Now let us deduce the Gibbs-Helmholtz equation, which is an important equation in thermodynamics. So I have explicitly shown here the mathematical calculation to deduce the Gibbs-Helmholtz equation from Gibbs free energy. So we have considered two states, state 1 and state 2, and we have defined the Gibbs free energy for the two states. Then we have subtracted G1 from G2, and we got this one, delta G equal to delta S minus T delta S. Now we know that delta G equal dG equal to VdP minus SdT. So for constant pressure process, this term will be cancelled and we will get dG equal to minus SdT. So if we differentiate dG with T, we will get minus S. And for the two initial and final state, it will be S1 and S2. Now by subtracting, we will get d of G2 minus G1 dt at constant P is minus delta S. So if we substitute the value of delta S in this equation, we will get this beautiful equation called the Gibbs-Helmholtz equation. It has important implication in the study of electrochemical cell. So what are the criteria of spontaneity and condition of equilibrium? If delta G at constant Tp is less than 0, that is delta G for the process is negative, the process will be spontaneous. At equilibrium, d delta G Tp equal to 0. With respect to Helmholtz free energy, it is the same condition, that is delta A at constant Vt should be less than 0 for a process which is spontaneous, and at equilibrium it will be 0. But for entropy, the entropy change should be greater than 0 for a spontaneous process and 0 at equilibrium. Now let's move on to the last law or third law of thermodynamics. Uh, Third law of thermodynamics basically gives the concept of absolute zero. It states that absolute zero is unattainable actually. So thank you all for listening to this video of thermodynamics. Goodbye. Thank you.